Hello everyone, welcome back to the channel. In today's video, we are starting a time series forecasting project using Python. This tutorial is made for absolute beginners, so everything will be explained slowly and clearly. Even if you are new to time series or forecasting, this video is totally safe for you. Before we jump into any code, we first need to understand what time series data actually is and why forecasting is so important in the real world. Once these basics are clear, everything else will feel much easier to understand. Time series data is data collected over time. Each value depends on a specific date or time. Examples: monthly sales, yearly profit, daily temperature. Time is very important in time series analysis. Why forecasting is important? Forecasting means predicting future values using past data. It helps industries plan better. Hospitals predict patient numbers. Banks predict transactions. Telecom predicts user growth. In this project, we will understand the dataset, build forecasting models, compare models, and predict future values. We will use 3 models: ARIMA, Aramax, Ceramax. Some beginners feel scared by words like stationarity, ACF plots, residuals, but these are simple tools to help understand your data and check model performance. By the end, these terms will feel easy and logical. Now that we understand the data and workflow, we are ready to start coding. Mount Google Drive in Colab. Here, we are connecting Google Drive with Google Colab. First, we import the Drive module from Colab. Then, we mount Google Drive inside the Content Drive folder. This step lets Colab access files stored in our Google Drive. After running the code, Colab asks for permission. Once authorization is completed, Google Drive is mounted successfully and ready to use. Installing required Python libraries. Now we are installing all the required Python libraries for this project. Each line uses the pip command to install a specific library. Here, we are installing pandas and numpy for data handling, seaborn and matplotlib for data visualization, SciPy and stats models for statistical analysis, and some supporting libraries needed for plotting and calculations. Running these commands makes sure all necessary tools are available in our Colab environment. After running the cells, Colab installs all the libraries successfully. Once the installation is complete, we can import these libraries and start working on our project without any errors. Importing required libraries for time series analysis. In this step, we are importing all the required libraries for our time series project. We import pandas and numpy for data handling and numerical operations. Seaborn and matplotlib are used for data visualization. We also import special time series tools like autocorrelation, decomposition, ARIMA, Ceramax, and exponential smoothing from stats models. These libraries help us analyze patterns, trends, seasonality, and build forecasting models. Finally, we import some statistical functions and random utilities that are commonly used in time series analysis. After running this cell, all necessary libraries are loaded successfully. Now our environment is ready for data analysis, visualization, and time series modeling without any interruptions from warnings. Importing dataset from Google Drive. Now we are importing our dataset into Colab. Here, we use pandas to read an Excel file from Google Drive. The file path points to the location where our dataset is stored. This step loads the data into a variable so we can work with it. After running the code, the Excel file is successfully loaded. The data is now available in the notebook and ready for analysis. Checking the data preview. Here, we create a copy of our dataset to keep the original data safe. Then, we use the head function to look at the first few rows of the data. This helps us quickly understand what the dataset looks like before starting any analysis. After running the code, The first 5 rows of the dataset are displayed. Now, we can see the structure, column names, and sample values from our data. Previewing the dataset. Now that we've loaded the dataset, let's take a quick look at it. We use the head function to display the first few rows of the data. This helps us understand the structure, columns, and sample values in our dataset. After running the code, the first 5 rows of the dataset appear. This preview gives us a clear idea of what the data looks like before we start analysis. Checking data description. Next, we are checking the summary statistics of our dataset. By using the describe function, we get information like count, mean, minimum, maximum, and standard deviation for each column. This helps us understand the overall structure and distribution of the data before analysis. After running the code, you'll see a table showing the summary statistics of all numerical columns. This gives a quick overview of the dataset and helps identify any irregularities or patterns. Checking for null values in the dataset. Here, we are checking our dataset for any missing values. The ISNA function identifies all the null values in each column and sum counts them. This step helps us know if there are gaps in our data that need cleaning before analysis. After running this code, we get a count of missing values for each column. If all values are 0, our dataset is complete. Otherwise, we can take steps to handle the missing data. Exploring the date column. Here, we are exploring the date column in our dataset. We use the describe function to get a quick summary of the month column. This will show information like the count of entries, the earliest and latest dates, and general statistics about the data. After running the code, we see a summary of the month column. This helps us understand the range and structure of our time-related data before we start any analysis. Setting month as index. Here, we are setting the month column as the index of our data frame. Using it as an index makes it easier to work with time series data and perform analysis by month. The in-place equals true parameter updates the data frame directly without creating a new one. After running this code, the data frame now uses the month column as its index. This makes the data ready for time series operations like plotting and forecasting. Preview the first 5 rows of the dataset. Here, we are checking the first 5 rows of our dataset using the head function. This helps us quickly understand the structure of the data and see the columns and values. It's a simple way to inspect if the data has been loaded correctly. After running the code, the first 5 rows of the dataset are displayed. Now, we can see the column names and some sample values, which helps us plan our next steps in analysis. Setting data frequency to monthly. In this step, we set the frequency of our time series data to monthly. Using the asfrec function, we tell pandas that each row represents 1 month. This is important for time series analysis, so that models like ARIMA or Ceramax can correctly interpret the data. After running the code, our data is now treated as monthly time series. This ensures that all future analysis and forecasting will follow a monthly timeline. Setting frequency and checking for missing values. Next, we set the frequency of our time series data to monthly using asfrec. This ensures our data is treated as a proper monthly time series. After that, we check for any missing values in the dataset using isna.sum. This helps us identify if any data cleaning is needed before analysis. After running the code, we get a count of missing values for each column. If the result shows zeros, it means there are no missing values and our data is ready for modeling. Checking for null values in the dataset. Next, we are checking our dataset for missing values. We use the ISNA function to identify any null values in each column and some to count them. This helps us understand if there's any missing data that we need to handle before analysis. After running this code, we see the number of null values in each column. If all columns show 0, it means our dataset is complete and ready for further processing. Visualizing the healthcare feature. Here, we are plotting the healthcare feature from our dataset to visualize its trend over time. We set the figure size for better clarity and use a purple color for the line. The x-axis shows the date, and the y-axis shows the healthcare values. This helps us understand the pattern and behavior of the healthcare data. After running the code, a clear line chart appears. We can now see how the healthcare feature changes over time, which is useful for analysis and forecasting. Plotting the telecom feature. In this step, we are visualizing the telecom feature from our dataset. First, we set the figure size to make the plot wide and clear. Then, we use the plot function on the telecom column and set the color to blue. We also add a title and label the x-axis as date and y-axis as telecom. This helps us see how the telecom values change over time. When we run this code, a line graph appears showing the telecom feature over time in blue. This plot gives a clear view of trends and patterns in our data. Visualizing the banking feature. Now we are going to visualize the banking feature from our dataset. First, we set the figure size to make the plot wider. Then, we select the banking column and plot it with a green color. We also add a title and label the x-axis as date and the y-axis as banking. Finally, we display the plot so we can see the trend over time. After running the code, a clear line graph appears showing the variations in the banking feature over time. The green line helps us quickly identify patterns, peaks, and dips in the data. Plotting the technology feature. In this step, we are visualizing the technology feature from our dataset. First, we set the figure size to make the plot wide and clear. Then, we use the plot function on the technology column and choose orange as the color. We also add a title and label the x-axis as date and the y-axis as technology, so it's easy to understand. After running the code, a clear line chart appears showing the trend of the technology feature over time. This visualization helps us quickly understand how this feature changes across dates. Visualizing the insurance feature. Here, we are plotting the insurance column from our dataset. We set a large figure size, draw the insurance values as a red line, add a title, and label both axes. Then we display the chart. After running this code, we see a red line chart showing how the insurance values change over time. Adding white noise to the dataset. Here, we are adding the generated white noise values into our data frame. We create a new column called WN and store the white noise data inside it. After running this line, the data frame now includes a new column named WN containing the white noise values. Summary statistics of white noise. Here, we are checking the summary statistics of the white noise column. This helps us understand its distribution, like the mean, standard deviation, and range of values. After running this, we get a statistical summary showing count, mean, standard deviation, minimum, maximum, and quartile values of the white noise data. Visualizing the white noise time series. Here, we are plotting the white noise data we created earlier. We set a large figure size, plot the WN column as a purple line, add a title, and label both axes. Then we display the chart. After running this code, we see a purple line chart showing random fluctuations over time, which represents the white noise. Autocorrelation plot for white noise. Here, we are checking the autocorrelation of the white noise series. We set the figure size, then create an autocorrelation plot using the WN column. We also add a title to clearly describe the chart and finally display it. After running this code, we see an autocorrelation plot where most values stay close to 0, showing that white noise has no strong correlation over time. Autocorrelation plot for healthcare. Here, we are plotting the autocorrelation of the healthcare feature. We set the figure size, then create the autocorrelation plot for the healthcare column using a specific color. Finally, we add a title and display the plot. After running this code, we see a chart showing how the healthcare values are correlated with their past values over different time lags. Plotting ACF of white noise. Here, we are plotting the autocorrelation function, or ACF, of the white noise we just created. We set the number of lags to 40, skip the 0 lag, and color the lines purple. This helps us see if there's any correlation in the white noise data over time. After running this code, we get a purple ACF plot showing that the white noise has no significant correlations across lags, as expected. Plotting ACF of healthcare feature. Here, we are plotting the autocorrelation function, or ACF, of the healthcare feature. We set the number of lags to 40, skip the 0 lag, and color the lines red. This helps us see patterns or correlations in the healthcare data over time. After running this code, we get a red ACF plot showing how the healthcare values are correlated across different time lags. Creating and plotting a random walk. Here, we are generating a random walk starting from 99. At each step, we add either +1 or -1 randomly to create the walk. We store all the values in a list and then plot the first 132 steps as a teal-colored line. This helps us visualize how a random walk evolves over time. After running this code, we see a teal line chart showing the first 132 steps of the random walk, illustrating the unpredictable movement of values over time. Plotting the first 150 steps of noise series. Here, we are plotting the first 150 values of our random noise series. We set a wide figure, draw the noise as a purple line, add a title, and label the axes as steps and noise value. This helps us visually inspect the randomness of the noise. After running this code, we see a purple line chart showing the first 150 steps of the noise series, which appears random without any clear pattern. Autocorrelation plot for random walk series. Here, we are plotting the autocorrelation of a random walk series. We set the figure size, use a blue line for the plot, and add a title and axis labels. This helps us understand how past values of the series are correlated with future values. After running this code, we see a blue autocorrelation plot showing strong correlations at multiple lags, which is typical for a random walk series. Checking stationarity with augmented Dickey-Fuller test. Here, we are testing if the white noise data is stationary using the augmented Dickey-Fuller test. We pass our white noise column to the addFuller function, which checks whether the data has a unit root or not. After running this code, we get several statistics. If the p-value is very low, it confirms that the white noise series is stationary, which is expected for random. Checking stationarity with ADF test. Here, we are performing the augmented Dickey-Fuller test on the healthcare feature to check if the data is stationary. The ADF test helps us know whether the mean and variance of the series stay constant over time. After running this code, we get test statistics and a p-value. If the p-value is small, it means the healthcare data is stationary. Otherwise, it is non-stationary. QQ plot for white noise. Here, we are creating a QQ plot to check if our white noise follows a normal distribution. We use the probplot function from sippy.stats and then change the QQ line color to red for better visibility. Finally, we add a title and display the plot. After running this code, we see a QQ plot where the points closely follow the red line, confirming that the white noise is approximately normally distributed. Creating a QQ plot for healthcare. Here, we are creating a QQ plot to check if the healthcare data follows a normal distribution. We set the figure size, use probplot from SciPy, and customize the QQ line color to blue. Finally, we add a title and display the plot. After running this code, we see a QQ plot where the blue line helps us visually compare the data distribution with a normal distribution coding. So now, we've completed the first half of our time series forecasting project. We understood what time series data is, explored the dataset, visualized trends, and checked for stationarity, which prepares our data for modeling. The next step is building forecasting models like ARIMA, Aramax, and Ceramax, comparing them, and generating future predictions. Instead of making this video too long, I've uploaded the remaining code, full notebook, dataset, and project resources on Aionlinecourse. You can find everything in the projects section there. You'll get complete source code, dataset download, model building steps, forecasting results. So if you want to finish this project, go to Aionlinecourse and open this project from the projects page. The link is in the description below. And if you would like me to make a part 2 video explaining the modeling and forecasting step by step, comment part 2 below and I'll make it for you. See you in the next tutorial.